Thank you for joining us today. My name is Maureen Price, and I will be the moderator for our presentation. I am the leader for Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success. As with the other webinars, this will be a technical presentation intended for anyone who is interested in starting a discussion about the challenges that industrial facilities face in setting their operating and strategic plans. We will discuss what some solutions to those problems might be and what to consider when electrification is on the table. There will be a focus on the major systems that are impacted, what to look out for, including a few examples and case studies. Primarily focused on existing facilities, there is, however, a brief discussion about new design considerations. Everyone from mechanical process and utility engineers to environmental compliance to reliability and operations staff will benefit from this discussion that we will have this morning. James Turner is an executive process director with over 30 years at Fluor. He has managed the process design for many refinery and petrochemical projects over the years and has published and presented more than 25 technical articles about process design and project execution. James is an avid cyclist and tries to find a way to ride wherever he is located. He's done the MS 150 ride from Houston to Austin more than 10 times, and he's done the Tour de Rouge ride from Houston to New Orleans twice. Giovanni Parra is an electrical engineer with over 40 years of experience in oil and gas, power generation, and mining projects. He is a senior member of IEEE and is a registered professional engineer in the states of California and Alaska and in the province of Alberta, Canada. He is currently the vice chair of the refining subcommittee for the IEEE IAS Petroleum and Chemical Industry Committee. Giovanni enjoys tennis, swimming, and traveling around the globe in his spare time. He has lived in 5 countries and visited more than 40.
Thank you, Maureen. I'd like to lead off the presentation by asking you a few rhetorical questions. Is your facility facing any of the following problems? Is it operating at its peak energy efficiency? Are your steam generating systems and turbines becoming obsolete and requiring ever-growing maintenance needs? Are you looking for ways to reduce NOx or other emissions for local regulatory compliance? Are you looking to expand your facility, but your utility systems are maxed out, or worse, out of balance? Do you want to rebalance steam and electricity usage, but are concerned about what to do with excess fuel gas? Does a facility-wide energy optimization sound intriguing, but also intimidating? Lots of question marks, and especially because everything is linked, it might be intimidating to start to change things. Where to start and what are the knock-on effects on existing systems, including the flare? However, in this presentation, we'll show you that, properly applied, electrification may help you address many of these challenges and really future-proof your asset. Today, I will be talking about electrification of industrial facilities, which simply means designing new or revamping existing facilities to use more electricity instead of steam and fuel gas for your energy needs. So let's answer these questions one by one. Is your facility operating at its peak energy efficiency? Many operators see a noticeable improvement in their energy intensity index from electrification. The calculations are based on efficient electricity production compared to less efficient steam boiler production. Improvements in energy intensity are often part of a facility's strategic plans and goals and can have a noticeable impact on their operating costs. Are your steam generating systems and turbines becoming obsolete and requiring ever-growing maintenance needs? Owners may have steam boiler maintenance and equipment replacement or emissions requirements that will require investment. Some of this investment may be better spent on electrification. Overall reliability may increase, which can have a big impact to the bottom line. Are you looking for ways to reduce NOx or other emissions for local regulatory compliance? You may be facing looming environmental regulations that will require investment in new SCRs for your steam boilers. An electrification project can reduce your steam demand, therefore reducing the cost of environmental upgrades. This can be even more significant when you consider that emissions reductions from electrification may fit well with other strategic plans that could cause increases in emissions from process heaters. The emissions reductions in the steam system can be used to offset increases in other heaters. It's not just about NOx. SOx and particulate matter emissions can also go down, producing credits that can be valuable for your other strategic goals. Are your utility systems maxed out, or worse, out of balance? If you have limitations on your steam balance, cooling water balance, or natural gas import, you may not be able to expand or do other projects without doing some electrification. Can you purchase electricity for a lower cost than import natural gas? If so, this can also reduce your operating costs. Do you need to rebalance the steam and electricity usage, but are concerned about what to do with excess fuel gas? There are potential synergies in executing an electrification project with a project to increase LPG recovery from the fuel gas system. I'll discuss this in more detail later in the presentation. Burning less fuel already means that you'll make less CO2, which is a strategic driver for many companies. But by recovering more LPG and heavier material from your fuel gas system and replacing it with import natural gas, you'll further reduce CO2 emissions, even if your fired duty does not decrease. In most markets, LPG products and other liquid products are much more valuable than replacement import natural gas, so there can be a good benefit to the bottom line in addition to the CO2 reduction impact. Lastly, does a facility-wide energy optimization sound intriguing, but also intimidating? If you're planning a strategic reconfiguration based on shifting crude supply and/or market-driven product changes, that may be an opportunity to replace aging steam-driven compressors with new motor-driven compressors that have a fit-for-purpose duty specification. It's important to remember that electrification is a solution to the many opportunities to optimize your facility that you may be facing. Each of the opportunities discussed have a set of economics that justify the solution that you ultimately choose. One thing they may all have in common is LCFS, our low carbon fuel standard credits. The low carbon fuel standard is a rule that's been enacted to reduce the carbon intensity, or CI, in transportation fuels as compared to conventional petroleum fuels, such as gasoline and diesel. The purpose of this standard is to decrease the carbon dioxide emissions that are associated with vehicles powered by various types of internal combustion engines, while also considering the entire life cycle, oil well to wheels, in order to reduce the carbon footprint of transportation. Originally enacted in California, there are now local and national mandates in several countries and regions around the world. Fuels that have a lower CI than the target established by the regulatory agency will generate LCFS credits. Produced fuels that do not meet the target generate a deficit that must be offset with enough credits from generation and/or acquisition to stay in compliance with the standard. The most common low-carbon fuels are alternative fuels and cleaner fossil fuels, such as natural gas, CNG, and LNG. But these are not yet in widespread use as transportation fuels. They can have a very low CI if they're derived from biogas. Hydrogen can also have a low CI, but many factors contribute. Look for a future webinar on this topic. Hydrogen currently has a very small contribution to the total fuel pool, and there's not currently a well-developed fueling infrastructure. It has a relatively high cost, and hydrogen-powered vehicles are still somewhat experimental. This webinar is not going to go into the intricacies and applications of these standards. That's a whole other topic. Suffice it to say that the LCFS credits can improve your project economics as you seek to improve your plant efficiency. We can work with you on any specific questions that you have offline. Each scenario is unique and requires analysis and discussion. For any project, the capital cost is an important factor, but there are other factors that should be considered so that you know all of the impacts to the project are understood and accounted for. Any electrification project is likely to have secondary impacts to your utilities in addition to the direct impacts. We've helped several clients with this effort on past projects. Some challenges may appear overwhelming at first, but our team of experienced, practical engineers can help untangle the string so that all of the impacts, both positive and negative, to the utility systems are understood. Of course, any electrification project is going to have an impact on the electrical system in the facility. Giovanni, why don't you talk a little bit about the high-level electrical impacts?
Thank you, James. You're correct. It will impact the electrical system. Depending on the electrification requirements, the impact could be manageable by the existing electrical infrastructure. But the reality is that most facilities have limited or no spare capacity, so will require reconfiguration of the electrical system, new infrastructure, such as new substations, and all the upgrades may potentially impact the operating facility. I will provide more detail later in the presentation. Back to you, James.
Thank you, Giovanni. Now let's talk briefly about what other utility systems may be impacted by an electrification project. For a project where steam-supplied energy is being replaced by electricity, the obvious impacts to the steam system and power are electricity. For steam, there would be less overall steam demand if steam drivers are replaced with motors. However, it's important to understand the total impact to the steam balance at the various steam levels in your facility. Specifically, if you're long on low-pressure steam and have back pressure turbines that produce a lot of this low-pressure steam, replacing these drivers with a motor can be a big benefit. Conversely, if you need all of the low-pressure steam created by a back pressure turbine, replacing it may not have much value, if you would then need to let down more steam across a control valve to balance your needs. There may be significant impacts to other utility systems as well. The fuel gas system will frequently be impacted. If fired heat is being directly replaced by electricity, that's a reduction in fuel gas consumption. Likewise, if steam is replaced by electricity, that will also end up reducing fuel gas consumption in the steam boilers. The water system can also be greatly affected by an electrification project. If you replace condensing steam turbines with motors, this may have a significant reduction in cooling water demand, debottlenecking this utility and reducing water makeup to the cooling water system. Steam demand reduction can also lead to a reduction in the boiler feed water system, including the deionization, deaerator system, and the boiler feed water pumps. The challenges of a major program that includes electrification may appear daunting. We can help you identify the best options that will improve your operating costs and help you achieve your strategic goals. The challenges associated with electrification can be overcome or mitigated. We know what these challenges are from working on many complex projects, and we know how to address these challenges. If you're not sure where to begin, we can help you develop a plan that starts with a small strategic study to determine your current status and where the potential heavy hitters are that can make a difference. So what are ways that industrial facilities can electrify? There are three primary ways that can be considered. Heat pumps instead of reboilers and condensers for distillation columns, electric heating instead of steam or fuel-fired heaters, and electric motors instead of steam turbines. All three of these can be important and have large impacts in the right situation. A fourth related concept is utilizing a cogen-type facility to produce electricity and steam, instead of using import electricity and steam boilers. We'll discuss this option briefly in a bit. So let's talk about these three items in a little bit more detail. I'll start with the first one. using a heat pump designed to power the reboiler and condenser in a distillation column. Historically, these designs have been called heat pumps. They're also called mechanical vapor recompression, or MVR. Heat pumps use a compressor to compress the overhead vapor from a column to a high enough pressure that the condensing temperature is now above the temperature required to reboil the bottom of the column. Then the compressed vapor can be used as a heat source for the reboiler, while at the same time using the bottom of the column as the cooling source for the overhead condenser. Shown is a simplified sketch of the concept. It's also possible to design a distillation heat pump with a separate fluid and a closed loop that is compressed, condensed in the reboiler, further cooled by dropping the pressure across a valve, and then used to cool the overhead condenser. But all the examples I've seen in industry are like the example shown here, where the overhead vapor is the heat pump fluid. Heat pumps can have significantly better energy efficiency than traditional reboiler condenser systems, and save on both the reboiler side, which is often steam, and the condenser side, which is often cooling water. Energy intensity reductions of up to 90% are reported in the literature. Heat pumps work very well for systems that don't have a big temperature difference between the top of the column and the bottom of the column. Propane-propylene splitters are a good example of this type of column. There are similar advantages for ethane-ethylene splitters and steam cracker units and isobutane normal butane splitters. There are also applications in aromatic complexes and methanol production. For most other distillation separations used by refineries and petrochemical complexes, the much larger temperature change across the column significantly reduces the value of the heat pump approach and makes it impractical. This idea appears to be best suited for a new design, as it would be a major revamp to retrofit an existing column with a heat pump. Looking at the scorecard of impacts, this idea can reduce fuel, steam, and water consumption, reduce emissions, and improve efficiency, with the cost of higher electricity demand. Now let's talk about the second item. For steam heating needs, there are two ways to electrify. Either replace a steam heater with an electrically heated exchanger, or replace a fuel-fired steam boiler with an electric boiler. Shown on the right is an electric heater. Steam and condensate piping and controls are replaced by electrical supply, which may reduce maintenance expenses and reduce capital costs for a new facility. One advantage of a steam exchanger is that the maximum temperature is self-limiting. You can't heat the process up to a higher temperature than the condensing temperature of the steam. An electric heater will not have this same intrinsic feature. Controls must be designed to provide protection against overheating the process for upset, low flow, and blocked-in scenarios. Like the heat pump, this concept can reduce fuel, steam, and water consumption, reduce emissions, and improve efficiency, with the cost of higher electricity demand and potentially less temperature controllability. Shown on the right is an electric steam generator sold by Stork. It may be a good option for a revamp of an existing facility. You can reduce your current emissions from steam generation while still supporting all of the existing process needs with steam. Note that many processes use live steam injection into the process, so it's not practical for these processes to replace all of your steam needs directly with electric heaters. This is an advantage of an electric boiler. It can address steam injection and steam heating needs. This concept can reduce fuel consumption, reduce emissions, and improve efficiency with the cost of higher electricity demand. Now I want to talk about the third idea on the list, using electric motors instead of steam turbines for large compressor and pump drivers. We've helped U.S. refiners look at the impact of replacing large steam turbine drivers with electric motors. This has resulted in positive projects at multiple refineries. Improved energy efficiency, reduced emissions, improved reliability, and lower water consumption have been obtained, and some refiners have avoided additional steam boiler investment. The project can impact the power infrastructure, steam, fuel gas, and cooling water systems, as well as potentially impacting ISBL controls and relief systems. If replacing the driver makes sense, you may want to consider if installing a whole new compressor is a good option. If there is an adequate plot space available, installing a whole new compressor with an electric motor may not cost more when the cost for doing work during a turnaround versus new construction outside of a turnaround is considered. This can also allow you to replace an aging compressor with a new compressor and potentially optimize it for your current operation instead of the way the unit was operated decades ago when the compressor was originally specified. Looking at the scorecard of impacts, this idea can reduce fuel, steam, and water consumption, reduce emissions, and improve efficiency with the cost of higher electricity demand. However, as we'll show on the next slide, consideration is necessary when changing to electric motors that you understand the impact on compressor operation that fixed speed rotation might have. Of course, there are solutions available to mitigate that impact, such as controls modifications and variable speed options. And as previously discussed, this may impact release scenarios and flare loads. One item that needs to be considered when replacing a steam turbine driver with an electric motor for a centrifugal compressor is the potential impact on the operating speed. Shown here is a typical compressor curve that can operate at different speeds. Steam turbine drives have an inherent ability to change speeds, which can provide more flexibility and operability for the compressor to manage changes in gas molecular weight and flow requirements. When replacing a steam turbine with a fixed-speed motor, this impact needs to be carefully considered. The variation in process conditions, particularly the gas molecular weight, must be evaluated. All possible operating conditions should be considered. Compressor surge and spillback controls may require modifications to satisfy requirements, and energy consumption may increase for some cases due to excess flow or pressure being produced by the compressor. The suction throttle valve and spillback valves may need to be modified or replaced to provide the flexibility that was previously provided by varying the turbine speed. These issues can almost always be addressed, but they need to be considered. Of course, installing a variable speed motor is an option, but for large motors, there's usually considerable additional cost and space required. A better option may be to install a variable speed gearbox to convert the fixed speed motor to different speeds as required to optimize the compressor operation. We have the process, mechanical rotating equipment, and control systems SMEs to help clients evaluate how their particular process might be impacted by replacing a steam turbine driver with either a fixed speed or variable speed option. I talked a bit ago about some of the high-level utility impacts. I'd like to now go into a little bit more detail on a few of them. Electrification can have a big impact on the steam balance, which can have a big impact on the fuel balance. Replacing any fuel gas fired heaters with electric heaters will also have an impact on the fuel gas balance. Many refiners run close to fuel balance and would be long on fuel gas if they do the electrification that they want to do. If this is an issue, there may be options for recovering more LPG and heavier material from the fuel gas pool, or possibly make less material that ends up in the fuel gas system. Projects to increase C3+ recovery in gas plants can have a very good payout in selling more LPG product and also support efforts to electrify. If this option is pursued, product storage and transfer logistics will need to be understood so all the requirements are addressed. You may also be able to reduce the amount of heavy material that ends up in your fuel gas system by making changes in conversion units, such as hydrocrackers and FCC units. By changing the catalyst and operating conditions, you can crack less and make less material that ends up in the fuel gas system. If you're making changes to reduce the amount of LPG material in your fuel gas, you'll need to understand how this can affect the heating value of your fuel gas. Replacing LPG with methane will lower your heating value, so you'll need to understand if you have heaters that would have fuel gas hydraulic issues with a lower average heating value. Many large steam turbines are condensing turbines, which usually use large cooling water surface condensers. Replacing these turbines with electric motors can lead to a significant reduction in cooling water requirements, which can have a very beneficial impact on operations, It debottlenecks the cooling water system, possibly removing other operating constraints, and can reduce cooling water makeup consumption. In some cases, entire cooling towers may be able to be shut down, further reducing power consumption for cooling water pumps and improving the facility visual appearance. Steam demand reduction can also lead to a reduction in makeup boiler feed water, so there can be a double impact in reducing water consumption at the facility. Water consumption is often a major expense for an operating facility, so this can also have a large impact. Here are a few examples that show the potential impact of replacing a steam turbine driver with an electric motor for the electrical, steam, and fuel gas systems. There are two main types of steam turbines, condensing and back pressure. There are also condensing turbines that extract steam at one or more intermediate pressures. Condensing turbines exhaust the steam at a very low pressure, at a vacuum, well below atmospheric pressure, and the steam is then condensed into water, usually in cooling water exchangers, although air coolers are sometimes used. Back pressure turbines take a relatively high pressure steam, say 600 psig, and exhaust at a lower pressure, say 150 psig. Since there's much more energy in 150 psig steam than steam at a vacuum, a much larger steam flow rate is required for the same driver load for a back pressure turbine compared to a condensing turbine. So back pressure turbines are a good fit for a facility if there's demand for the lower pressure steam. However, if your demand for the low pressure steam has changed over the years, the existing turbine may be producing a lot of low pressure steam that you really don't want. This can provide a good incentive to replace that turbine with an electric motor. We've seen simple payouts of 2 years or less for capital projects for replacing condensing steam turbines with electric motors, if incentives for reduction in the CO2 emissions are included. Payouts can even be significantly better than that if capital projects for steam system upgrades for reliability or environmental compliance are reduced due to the electrification project. Another option that could be considered is installing or expanding a cogeneration unit. These units convert fuel into electricity and a heat source, typically steam. These systems are now often called CHP, for combined heat and power. While cogeneration units have been in use for some time, modern CHP facilities using turbines can achieve much higher efficiencies, as turbine technology has improved over the decades. The graphic here from the US EPA shows the net fuel cost lowered by use of CHP. Installation of a new CHP is a significant capital investment, and one key factor in this decision might be if an existing boiler required significant updates to meet modern emission requirements. This shows particular value when one or more steam boilers can be decommissioned after electrification to reduce steam demand and add CHP instead of a major boiler upgrade. As previously mentioned, if a facility has plans to replace a significant amount of steam consumption or steam generation with electrical energy, it may be long on fuel gas. Most refineries and petrochemical complexes have units that produce methane and/or hydrogen that may not have a good home if it's not used to generate steam. A new cogen unit can become the sink for this produced fuel gas. If CO2 emissions are a concern, adding a carbon capture system to the cogen may be a good way to address this issue. There are some Innovation Builders webinars specifically on this topic. A design for a new facility can use any of the ideas that we discussed for revamping existing facilities. Are there other ideas that could be used for new facilities that may not be practical for revamps? A lot of people are looking at this. Let's take the example of a naphtha steam cracker that produces ethylene, propylene, and aromatics, primary building block chemicals used for plastics production. The reaction takes place at a high temperature, typically about 850 degrees centigrade, and it's an endothermic process, so you need to add a lot of additional energy to keep the reaction going. A lot of attention is focused on this topic. BASF has announced they're investigating designing an all-electric heated naphtha steam cracker, and Shell and Dow have announced a joint venture to develop an electric heated steam cracker. We've done some calculations. For a typical naphtha steam cracker that makes 1,500 kTA of ethylene, 1,400 megawatts of absorbed duty would be required to provide the reactor heat. So this unit would require electrical consumption similar to what many large commercial power plants produce. This is technically possible, but it will be expensive. BASF mentions looking to revamp existing units with electric heaters in the future. It seems this would be a major and costly revamp. It might be more applicable for a new unit design. If your goal is to produce the steam cracker products with minimum CO2 emissions, there are some other options. One option would be to use a fired heater, but use hydrogen as the fuel. This is assuming that the hydrogen is either green or blue hydrogen and had minimal CO2 emissions during its production. Calculations show that 460 kTA of hydrogen would be needed to provide the fuel for our 1,500 kTA steam cracker, equivalent to 530 million standard cubic feet per day. Also technically possible, but costly. It may be possible to revamp existing units that use fuel gas to use hydrogen fuel, but would likely require infrastructure and fuels controls changes. There's a third option that may be the best choice. Use fuel gas as is done in all steam crackers today, but capture the CO2 from the flue gas. This technology is available today. In fact, Fluor licenses such a technology, the Economine FG Plus process. Of course, you need to have a disposition for the recovered CO2 for this option. With the first and second options, a major issue is, what do you do with the methane produced by the steam cracker process? Steam crackers produce a lot of methane as a side product. In existing units, this gas is burned in the process heaters. If the heaters are electric, this methane needs to be sent somewhere else. There may be synergies with an electric steam cracker combined with a GTL or gas to liquids process to convert the methane to a liquid product, or possibly with a syngas operation to make methanol or hydrogen. For the second option with a hydrogen-fueled heater, the methane could be converted to hydrogen, but you're still expelling the CO2 unless you recover it in the hydrogen generation process. You might be better off just going with the third option and recover the CO2 from the flue gas directly. In summary, there are ideas and options available, but the best choice may depend on what your goals are and on location logistics. Giovanni, why don't you talk a little bit more through the electrical infrastructure impacts to electrification?
Thank you, James. In our experience, the selected process loads that are converted from steam to electricity require large motors, such as the 12,000 horsepower example on a previous slide. We have seen loads ranging from 5,000 to 20,000 and even larger. Motors of this size have a strong impact on the electrical system, which needs to be studied carefully, as most facilities have limited spare capacity or were not designed to support these large loads. To start, there are three key electrical system studies to be performed to assess the system: low flow, short circuit, and motor starting. These are complex studies that can be performed by an experienced Fluor electrical engineer using commercially available electrical analysis simulation software, such as ETAP, SKM, and others similar. Each of these studies will help you with the assessment of your system. Basically, you need to know if you have the capacity to support the new load, if the existing equipment is ready to support the additional motor load contribution, and finally, can the motor be started without impacting the system voltage? One option to start large motors is to use reduced voltage starting methods, using auto transformer, capacitor, reactor, or even an adjustable speed drive like you mentioned before. Next, when electrical systems is assessed, you will be able to define the upgrades of the electrical infrastructure. These upgrades may include additional utility power, including new transmission lines to take delivery of power at a higher voltage. The new lines may be 34.5, 69 kV, or even higher. or if the facility has a cogeneration plant, expanding it with new generation. The new electrical configuration will impact equipment in the main and unit substations. Most likely transformers, switchgear, and other power equipment will require upgrades. The new electrical system will likely have dedicated substations for these large loads. Let's not forget the impact to the facility underground and above ground electrical infrastructure and the associated impacts to pipeways and other structures that need to support the new conduits or trays that will feed these loads. Lastly, design must consider construction and cutover challenges. Since this is all being done in an existing operating facility, the electrical upgrades need to be well planned. Electrical work requires equipment to be de-energized, so the tendency is to schedule the work during a turnaround or doing a scheduled maintenance to minimize the impact to the operating facility. That imposes a significant constraint to the project schedule. As you can see, James, the electrical infrastructure is also a key factor to be considered for electrification projects. Back to you.
Thank you, Giovanni. So how can an operator determine what to do? Develop an accurate power, steam, and fuel gas balance for your facility. Consider upset and other operating cases, such as when individual units are shut down for maintenance. Understand the reliability of the existing systems and what outages have a big impact on operations. Are there steam boiler replacement or reliability improvement projects being considered? You may be better off figuring out how to decrease steam consumption instead of spending money to make your current system more reliable. Understand what your cost is for incremental power purchased and import natural gas. You'll need to understand what upgrades of the systems within your facility will be required, but should also be aware of possible infrastructure impacts to your across-the-fence electrical supplier. Understand which current or future emissions requirements, including carbon footprint, may have on a facility. These requirements could be both regulatory-driven or internal company requirements. For example, if existing steam boilers will require the addition of NOx removal equipment, this can provide an opportunity to build a new, smaller, more efficient and more reliable steam boiler system for not much more than the regulatory revamp cost. Similarly, if there are steam boiler reliability upgrade projects planned, decreasing steam consumption instead of implementing a boiler replacement or reliability upgrade project may be a good option. In conclusion, to find the best project for your facility, you should start with high-level goals, develop a good understanding of where you are, compare options, understanding which parts are independent and can be evaluated individually, and which parts are interrelated and need to be considered as a group. You'll want to understand the benefits, the reduction in operating cost, improvement in energy efficiency, and reductions in emissions and water consumption. And of course, you'll need to understand the cost, the capital cost to implement changes, systems upgrades required, both within the facility and by outside suppliers, and the process ISVL and OSVL impacts, both positive and negative, for each option. After all, it doesn't help you if a preliminary study makes an option look promising, but impacts that were not initially considered make the option much more expensive or not practical. Fluor has a long history of helping our clients perform these types of studies. We have the experience, tools, and expertise to help look under every rock, both to find hidden opportunities and to discover all the impacts, both positive and negative, for each option. If this sounds intriguing to you, please contact us and we'll discuss your specific situation and how we can help you find the right solution. With that, we'd be happy to address any questions or comments that you have.
Thank you, James and Giovanni. Let's take a minute and address the questions that have come in. Just a note to everyone on the line, please do submit your questions to all panelists so that we can include them in the next 15-minute Q&A period. The first question, does electrification make sense if my facility does not receive an economic benefit for a lower carbon footprint?
Thanks, Maureen. I'll take that question. The first electrification project I worked on was to replace a steam driver in a Louisiana refinery over 20 years ago. The value for the project didn't have anything to do with reduced CO2 emissions. It was driven by improvement in the steam balance and the cost benefit they received from buying electricity instead of import natural gas. So yeah, electrification can make sense in a lot of cases, even without the economic credit for reduced CO2 emissions.
All right, great. Next question. When replacing a compressor driver with an electric motor, you mentioned available existing plot space. If plot space is not available, is it still probable to be cost-effective if a plot relocation of the compressor is required to change the driver?
Okay, thanks, Maureen. I'll take the first part of that. If you're replacing a steam turbine with an electric motor, our experience has been that just for the driver change, that there's usually plot space available to do that and put it with the existing compressor. Where you wouldn't have typically space right there is if you're putting a new compressor with a new motor in and want to do it outside of a turnaround. And so we've looked at cases where we've found a place nearby to the unit that's close enough to put a new compressor and the new electric motor. Then you have to run your process piping, further. So there's a trade-off to look at it, how far you have to modify the process piping for a new compressor versus just that. And in some cases that may drive clients to say, okay, we'd like a new compressor, but we don't have a place to put one. So we'll just go with the driver change and leave the compressor as it is. You could also probably put in a new compressor with a new motor, but in the same space. But to do it all during a turnaround, unless you're planning for the unit to be down for a long time, that would be really expensive. And Shaker, I don't know if you have anything you want to add to this.
Yes, this is Shaker Kambadi. So we have looked at both of those options recently, and that's very true. We kind of find that it's easier. You can always find a plot space nearby, and replacing instead of just doing a driver replacement, just taking a look at the entire compressor, driver, both combination, and putting it before the turnaround comes out to be a lot more cost effective. Not only the efficiency gain that you gain from the compressor, you also gain the risk involved in doing the turnaround that diminishes. At the same time, you're basically all you're doing is time doing a turnaround. So yes, that's been the most success story so far. But that doesn't mean that that's the only option. I mean, we can still look at it at the same spot if the space is available.
Thanks, Shaker. We have another question. Can a variable speed driver be more efficient than a fixed speed motor?
Yes, a variable speed driver, whether it's a steam driver, variable speed motor, or variable speed gearbox connected to a fixed speed motor, can be more efficient than a fixed speed motor. The speed can be optimized for the current process conditions instead of producing too much head that's lost across a control valve, or too much flow which is spent across a spillback valve. But it's important to look at the total energy efficiency impact of the whole system, including the energy generation source. If electricity production is more efficient than steam production, replacing a steam turbine with a fixed speed motor may still be more efficient overall.
All right, great. Thank you, James. Here's another one. What are the typical energy efficiencies for electric steam boilers compared to natural gas-fired boilers?
Shaker, would you be a good one to respond to that?
So the electric, I guess the steam boilers are typically anywhere between 85%, depending upon somewhere around 85% on the steam boiler. I guess the question was on the compare that to the electrical boiler. Is that what it was?
That's correct. Thank you.
No, as far as we looked at some electrical boilers, we didn't quite, I don't remember the exact efficiency that there was, but I think
we can look that up and
yeah, we can look it up and let you know, right?
Absolutely. Terrific. All right, here's the next question. And by the way, I hope you have your thinking caps on because the questions keep flying in. Have any mechanical vapor recompression projects proved economical for overall energy efficiency improvements?
Well, the example I gave of a heat pump is there's other types of mechanical vapor recompression, but I focus specifically on distillation heat pump, and those are known to be very much more efficient than traditional designs. And the classic example is in a propane propylene splitter, where I think pretty much all modern units are designed with the heat pump concept. So it's definitely more efficient for those applications. As I discussed, if you have a column where there's not a close temperature range between the top of the column and the bottom of the column, then it becomes, I think, impractical or not really feasible, because you would need to compress your overhead to such a high pressure, or your temperatures get so high that it's not practical or economic.
All right, great. So here's another question. Can we help clients with economic comparisons of the change in their operating costs for changing utilities? And then what other services are expected that you have to look at for an electrification assessment?
Well, many clients have a basis for utility cost, such as the cost per gallon for cooling water or per pound for steam, that they use for utility studies. If they don't have that, we can help them either based on typical values from past projects or by studying their existing operating costs and so forth to estimate what their costs are to do those calculations. And we can also, of course, help them understand capital costs for any options that they're looking at.
All right. Good answer. Here's another one. Do you see electrification replacing steam heat, that it will still have the rapid shutdown capability? So in other words, this is worded a little bit differently. Will electrification have the same rapid shutdown capability when compared to steam?
I think for some applications, that's something that that would have to be looked at. We'd have to talk to, I guess, the electric heater vendors and to our mechanical SMEs to tell us for a specific application and design, once the power is shut off to that electric heater, how quick does that dissipate? Whereas, I mean, you in both cases, even with the steam exchanger, you've got all of the exchanger that's at the temperature that you're operating at. So when you cut the steam supply, you don't immediately lose heat input. But that's something that we'd have to look at for specific cases, I think.
Okay, let's see. There's so many questions are filing in. Okay, here's a good one. And I'm going to send this one to Shocker. Shocker, have you found dynamic simulation valuable to consider the mode and state transitions in the process in an electrification project?
So yes, we did. I think dynamic simulation has certainly a place in reducing the flare load. So many times when, as James kind of pointed out in the presentation, that the flare needs to be looked at, and in many cases, if the steam and power did not occur simultaneously in your flare load, and all of a sudden you change out the turbine to an electric driver, your flare load could go up. And so, basically that would have an impact. And so going through the dynamic simulation would help you kind of establish that, whether you can reduce the flare load via dynamic simulation. Because most of the time you find that a lot of this flare load calculations have been done with very conservative assumptions. And dynamic simulation helps us kind of minimize some of that ambiguity or some of the assumptions that we made in coming up with the flare load.
Thanks, Shocker. As someone who started her career doing dynamic simulations, I like that answer. Here's another question, and I'm going to address this one to James. How much space is needed for a variable speed versus a fixed speed motor?
Well, I think it depends on the size. My understanding, and I'm not a motor expert, but that under 600 horsepower, that there's not much size difference. But as you get into much larger motors, then you end up with needing a lot more space for the variable speed motor.
All right, terrific. Here's a question for Giovanni. Has Fluor ever encountered asynchronous harmonics issues when dealing with these types of electrification projects?
Interesting question. I don't have an answer, but that's part of the simulations that we have to run. That's part of the system studies that I mentioned before. That will be another one of those studies that we'll be doing prior to any decision.
All right, great. Here's another one for you. How does the electrical classification factor into the cost of new motors for an electrification project?
I think in general, not significant, because in most cases, oil and petrochemical installations, fall in a class 1 div 2 hazardous area classification. So it should not be much of an impact. Now, if the installation is going to be in a class 1 div 1, that will be very expensive installation and it's not recommended.
All right. Okay, here's another one. Does the economic benefit of electrification change if the horsepower becomes large enough to require a synchronous motor?
Good question. Potentially. A synchronous motor, depending on the site, could be, maybe 50% higher than the equivalent induction motor. So, that new motor has an exciter. It requires an excitation package, but at the same time has a benefit of a better efficiency. So if you consider the life cycle of that equipment, especially on motors 5,000 and higher, you get paid off. And in 20 years, I'm sure you paid it off. So that's the benefit of the asynchronous motor on a larger scale.
All right. Another question. If electrification is replacing back pressure turbines and the low pressure steam balance does not change, is there still an expected decrease in boiler demand?
So I'll take that. There could be a small decrease in boiler demand for the required lower pressure steam if it's desuperheated after it's let down across a control valve, since this would make a little bit more steam. But in general, if the lower pressure steam is needed, then replacing a back pressure turbine with a motor might not have a good payout because you're just going to be still needing to make almost as much steam and dropping that steam across a control valve.
All right. I think we have time for one last question. Is it possible that replacing a steam turbine with an electric motor, that CO2 emissions could actually increase if the electricity has a large component of coal-fired production?
I'll take that. I think all power companies calculate their equivalent CO2 emissions, and where we've executed these projects, that hasn't been the case. There's been enough renewable energy production that the electricity has a lower carbon footprint than the incremental natural gas and fuel gas that it replaces. So I suppose that could be possible, but we haven't seen that on the projects we've looked at. Shacker, do you have anything more to add on that?
No, I think you covered it pretty much. Yeah, okay. In fact, we have not seen that also. Pretty much we've seen in California, at least, that there's definitely a reduction once you purchase power from offsite.
Okay, so with that, we'll end our questions. Those of you that submitted questions that we didn't answer, we will respond. And I want to thank James, Shocker, and Giovanni for the time that you've spent today and in preparation for today's webinar. And thanks to our audience for attending. You've been very engaged, and it's been a pleasure being your moderator. We will be hosting our next webinar on Thursday, January 14th, 2021 at 9 a.m. Central, where Fluor's subject matter expert, Onno Pop, will discuss ISO 15926. You might be wondering what this standard is and whether it's important. This ISO standard defines a methodology for simplified industrial usage of reference data. In short, it's a standard for data exchange for the entire plant lifecycle across the process industry supply chain. It's a fascinating discussion, and I know you're going to want to hear what he has to share. Please keep in touch with your Fluor contacts, follow our social media postings, or head to the Innovation Builders page on fluor.com to register for this or other future webinars. Thank you again for attending. We will send out a compiled list of Q&As within a few days, along with a notification that the webinar recording is available for replay on fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back with you. From all of us on the Innovation Builders team, have a safe day. We'll see you in January.